This will be about the early influence and contributions from the east side of the world, especially from the Arabs and the Chinese. The immediate cause of the 7th century surge in Arabic power was the emergence of a new faith, Islam, founded on the teachings of Muhammad. United in religious fervor, the desert tribes of the Arabian Peninsula met few obstacles as they spread swiftly through the Mediterranean world. The historic city of Damascus fell to Arab arms in 635, as did Jerusalem in 637. Egypt was conquered between 639 and 642. Advancing westward, the Arabs crossed the Straits of Gibraltar in 711, moving up through Spain and into France as far as Poitiers. Meanwhile, Arab armies swept in the other direction, through Syria and Persia, even reaching northern India. 100 years after the death of Muhammad, his followers were the masters of an empire half again as large as was ever controlled by the Romans. Only Christian Europe, except for Spain, was barred to them. The rulers of the new empire, known as caliphs or successors, governed from Damascus. However, in 762, they resolved to build a new capital on the Tigris River, at a place that bore the old Persian name of Baghdad, quickly becoming a great commercial and cultural center. Baghdad boasted a population of 800,000 in the 9th century, making it larger than Constantinople. Arabic became the language of learning for a large part of the world. All Muslims were required to know it to read the Holy Quran, and anything written in Arabic carried the prestige previously accorded to Greek works. The intellectual legacy of Greece was the most important treasure of the lands that came under the domination of the Arabs, and the main task of Arabic scholarship was its absorption. To this purpose, Caliph al-Ma'mun set up the renowned House of Wisdom, a kind of academy comparable with the museum at Alexandria. An intense and energetic effort was made to acquire Greek manuscripts, even to the extent of sending out emissaries to Constantinople to secure a copy of Euclid's Elements from the Byzantine Empire. These were rendered into Arabic by corps of translators at the House of Wisdom and placed in a library there for the use of scholars. By the beginning of the 10th century, practically the whole extant body of Greek scientific and philosophical writings had been recorded in the Arabic language. This classical heritage, along with refinements and extensions that the Arabs developed themselves, was eventually to reach the Latin West. The most illustrious of the Arab mathematicians was Muhammad ibn Musa al-Khwarizmi. He is a close friend of Caliph al-Ma'mun, a court astronomer, and a scholar early associated with the House of Wisdom. It was largely through his work, consisting mainly of two books, one arithmetic and the other algebra, that Europe became acquainted with the Hindu numerals and the algebraic approach to mathematics. Al-Khwarizmi compiled a small treatise on arithmetic with the title something like "Book of Addition and Subtraction according to the Hindu calculation". It is the earliest work in Arabic to explain the use of the Hindu decimal system of numerals. Although Al-Khwarizmi mentions just 9 letters, or the symbols for the digits 1 through 9, to be used for writing numbers, he does also make use of 0. When nothing remains, especially in subtraction, put down a small circle, so that the place be not empty, but the circle must occupy it. No copies of the original Arabic version of the book have survived. It has reached us only in a Latin translation, Algoritmi de Numero Inderum, made by John of Seville at the beginning of the 12th century. Its influence on European mathematical thought was so great that the new numerals were misnamed Arabic, despite their Indian origin. In 1857, a copy of the Latin translation was discovered at the Cambridge University Library. It begins with the words "Dixit algorithmi", or "Thus spoke Al-Khwarizmi". Western Europeans first learned about algebra from the work of Al-Khwarizmi. The name algebra is the European corruption of al-Jabr, part of the title of Al-Khwarizmi's treatise Hisab al-Jabr wal-Muqabala. Apparently, the title means the science of reunion and reduction. The words refer to the two principal operations the Arabs used in solving equations. Reunion refers to the transference of negative terms from one side of the equation to the other, and reduction to the combination of like terms on the same side into the single term, or the cancellation of like terms on opposite sides of the equation. Algebraic rules of procedure were proclaimed as if they were divine revelations, which the reader was to accept and follow as a true believer. Whenever reasons and proofs were given, they were presented as geometric demonstrations. The Arabs, inspired by Euclid's Elements, seemed to believe that an argument had to be geometric to be conceiving. In dealing with quadratic equations, Al-Khwarizmi divided them into three fundamental types, with only positive coefficients admitted. Negative quantities standing alone were still not accepted by the Arabic mathematicians. All problems were reduced to the standard types and solved according to a few rules. Al-Khwarizmi's geometric demonstration of the correctness of his algebraic rules for solving quadratic equations may be illustrated by his discussion of the equation x squared plus 10x equals 39, a problem he solved by two different methods. This equation reappears frequently in later Arab and Christian texts, running like a thread of gold through algebras of several centuries. The first geometrical solution is explained as follows. Given x squared plus 10x equals 39, construct a square ABCD having sides of length x to represent x squared. Now one has to add 10x to the x squared. This is accomplished by dividing 10x into four parts, each part representing the area 10 over 4x as a rectangle, and then applying these four rectangles to the four sides of the square. This produces a figure representing x squared plus 10x equals x squared plus 4 times 10 over 4x. To make the figure into a larger square of sides x plus 10 over 2, we must add four small squares at the corners, each of which has an area equal to 10 over 4 squared. That is, to complete the square, we add 4 times 10 over 4 squared equals 10 over 2 squared. Then we have x plus 10 over 2 squared equals x squared plus 10x plus 4 times 10 over 4 squared equals 39 plus 10 over 2 squared equals 39 plus 25 equals 64. Hence the side of the square must be x plus 10 over 2 equals 8, from which it is found that x equals 3. In the general setting, the quadratic equation x squared plus px equals q is solved by this method of completion of squares by adding four squares, each of area p over 4 squared, to the figure representing x squared plus px to get x plus p over 2 squared equals x squared plus px plus 4 times p over 4 squared equals q plus p over 2 squared. This leads to the solution x equals square root of p over 2 squared plus q minus p over 2. For Al-Khwarizmi's second method of solving x squared plus 10x equals 39, the starting point is a figure composed of a square of side x and area x squared and two rectangles, each having length x and width 10 over 2. Because the area of each rectangle is x times 10 over 2, the area of the entire figure is x squared plus 2 times 10 over 2x. To complete this figure, so as to form a square, it is necessary to add a new square of area 10 over 2 squared. This area of the completed square is x plus 10 over 2 squared, and consequently, the square of x plus 10 over 2 is x squared plus 2 times 10 over 2x plus 10 over 2 squared, which is 64. The side of the square is then x plus 10 over 2, which is 8, whence the value of the unknown is x, which is 3. In solving the general equation x squared plus px equals q in this manner, a square of side p over 2 is added to the figure, which represents x squared plus 2 times p over 2x, thereby making the square of x plus p over 2, which is equal to x squared plus 2 times p over 2x plus p over 2 squared equal to q plus p over 2 squared. This yields, as before, the solution, where x is the square root of q plus p over 2 squared minus p over 2.